Water. We drink it.
That's some high-quality H2O.
We clean with it. We shower with it. We use it throughout our day.
But where does it come from? And how do they treat it before we use it?
We went to Edmond Water Resources Treatment Plant at Lake Arcadia to find out. There, we met with Utility Program Coordinator Jennifer Boaz and Plant Superintendent Roy Fife. Here we learned that Edmond, population 95,000, gets its drinking water from two primary sources. The city owns 56 water wells that pump water from the Garber-Wellington Aquifer. It also owns Lake Arcadia, which is the other primary source of water. The ratio of well to lake water can vary, but it's usually 50 to 60% lake water. Only water from Lake Arcadia is treated here at the water plant. During the winter months, they typically treat 7 to 8 million gallons per day. That goes way up during hard freezes because customers drip their pipes. During the summer months, demand is at its highest, and the plant processes 12 million gallons a day.
Let's see how they do it. Water intake.
First, the plant intakes water from the lake through a structure near the dam. From here, the plant is equipped with extensive treatment options designed to handle very challenging supply water. Thankfully, the water Lake Arcadia provides is much cleaner than anticipated when the lake was built in 1987. That means some of the cleaning processes can be bypassed during normal operation.
So here's a good overlay of the plant from what we see on SCADA. So right here's where the water comes in at from the intake structure. It comes in through low lift. We got the 4 pumps. Now we're not using these 4 pumps. We use these for during high flow. Right now the water's coming in, hitting a closed valve, going through the bypass, and coming to the plant. So it's all on gravity right now, which we save a lot of electricity that way during this time of the year.
Screening. The first equipment is in the screen building.
Raw water would come in from the lake from low lift or through the bypass valve, come in here. There were screens that would screen out some like sticks and stuff like that.
This equipment was in place to screen out large items such as sticks. It is currently being bypassed, which is not a problem because as the lake has matured, there's not as many sticks that come in, and those that do get taken out later in the process.
And here's kind of a layout of the raw screen building. We have 2 valves that are at the front that controls the water coming in from low lift. And it will say, well, if it's open 73% to get to your set point of 5.2 million. So these valves will adjust to get to a certain set point per where you want, how much water you want going through the plant. So the water comes across. What used to be the raw screens would come across. We have our flow measuring device here.
This is also the point at which water samples began being collected. A rigorous sampling program ensures safe, clean water is produced and monitors the plant performance. That starts here by testing the incoming water quality.
Flocculating clarifiers.
These clarifiers are large settlement basins. If the incoming water was high in suspended solids, they can be used to allow these solids to settle. Chemical treatment would have been added to help the solids clump up together, which is what flocculate means. That makes the solids heavier and causes them to sink faster. These clarifiers and the flocculating chemicals are being bypassed.
They never had to use it. It was part of the using of these clarifiers for the nastiest water when they first engineered it. So they didn't know what they were really going to get off that deep fork basin bottom, that river basin. So they were planning for like some really bad water, but it turned out to be a lot better than they had anticipated.
Ozone Generation.
Edmond uses ozone as a disinfectant. Not only does it disinfect, it is fast-acting, fast dissipating, removes color, odor, and taste, and oxidizes iron, manganese, sulfide, and organics.
The ozone, it's a little loud in here, but these were the first ozone units to be installed and used in the state of Oklahoma for drinking water.
So this is really the first, at this point, the first processing. What does the ozone do?
It's a disinfection. It starts basically breaking down and killing out your bad bacteria and different things in the water that can cause basically harm to humans. But it's the first process in that step in disinfecting the water. And it also aids with settling because it's a high level of oxygen. Because ozone uses oxygen and electricity, or to make ozone you use oxygen and electricity, combine them together, high voltage electricity, and creates ozone. Ozone naturally forms in the environment through oxygen in the air, and in lightning, you'll have, like after a thunderstorm or a big lightning storm, if you walk outside, you'll kind of smell the air's a little different. That's ozone in the air. And so what we basically done in here is we've taken what Mother Nature has created, we put it in a bottle basically, and we sped up the process to use it as a disinfectant. To create that oxygen gas is that we have liquid oxygen in both those tanks right there. And we feed oxygen across, it just feeds by gravity, and it's liquid, and it'll come to these, what kind of look like big radiators, and those are called vaporizers. So when the liquid oxygen comes in, it's very cold, but it starts vaporizing and turning into a gas as it goes up and down, and there's heaters on it. So it keeps it in a gaseous state as it pulls across and comes into ozone. When the gas comes in, it comes in contact with high voltage electricity, creating the ozone and giving off the gas. And it feeds out into these basins, just where I was showing you the two round wheel valves, where the water feeds in. There's basins in there, and basically there's air diffusers, ceramic, that create little bitty bubbles that give off the ozone in small bubbles for the disinfection. Oxygen is coming in here. It feeds in. We have an oxygen monitor that tells us what the oxygen is inside the room, so that way it doesn't get too high. So not necessarily high levels of oxygen would hurt you really bad, but it's something you got to monitor. So definitely we monitor our oxygen intake in the room. So our oxygen coming in is running around about 18 to 19 psi off the gauge. So it's feeding across. That oxygen comes in by way of this valve. It opens, and it feeds oxygen into the back side. The oxygen comes across from the cabinets over here or over here. You can see high voltage electricity. That's our power supply for the bulbs that come in. And so the electricity, if you look inside here, you can see some purpley looking light. That's the electricity going across the.
Once the ozone is generated, this pipe carries it to a manifold where it gets distributed to 3 places. 2 of the lines go to apply the ozone before the contact clarifiers, and 1 line applies another round of ozone post-clarifiers. We'll see those clarifiers in just a bit.
And we can kind of see how the ozone system is running from here. So this is how much we're putting out. Kind of here's kind of tells me what, how many degrees, how many hours it's ran. Kind of just gives me a basic overlay of, the oxygen in the room, how much parts per million are in the room of ambient ozone, if there was any leaks. So you can see there's nothing there, all zeros. But I can see everything in the ozone room right here as well. So we can monitor that.
Chemical room.
This room is for prepping chemicals that will be applied to the water. This includes lime, which softens the water, and polymers to help settle out unwanted particles and free chlorine.
We only saw the room through a window because the chemicals can be dangerous.
The lime and the polymers get added prior to the next stage.
Contact clarifiers.
The water that enters these clarifiers has been disinfected with ozone and has had the lime and polymers applied. The contact clarifiers give time for the chemicals to work, and they are specially shaped to promote settling and removal of unwanted particles.
Can you kind of see that blanket in there? Looks like a big cloud down there. Too bad the wind's blowing, because normally when it...
Too bad it's raining.
Oh, look, I found a fish. There he is.
Too bad it's not.
Is he really? There is.
Too bad the whole cloud.
I don't know what he is, but he's there.
The ozone didn't kill him?
Too bad.
Sometimes it does, sometimes it doesn't.
Too bad that
Sometimes they'll last in here months, they'll come over, and they'll go in the filters, and we have to dip them out, or we'll dip them out, and we can get them at the top here. That's why we always have nets. But you can tell if you look at the edge how clear the water is.
Oh, yeah.
And this is after settling. Like I said, this is where it mixes, settles, getting a lot of your organics to flow out, metals, different minerals.
Where do all those things go? Fall out.
Well, we do bottom blowdowns on those windows when they open, sends everything to drying beds.
Okay, that's how you're talking.
And it's like basically
That's coming out from here.
coming out from there, going down to there. So this is kind of like our waste. To the drying beds is kind of like our waste, like you would at wastewater. They said we probably said we waste off to keep our waste.
After it goes out the drying beds, what do y'all do to it?
We clean them out, we pile it up, we dry it out, spread it, fluff it, and we sell it to the farmers. So once the water leaves chemical mix, it comes out to your clarifiers, and you can see like we got this one on and this one online. And so basically here, we're just making sure that this valve's open, and then we check our sludge valves. And so sludge valves is what we're talking about, is those window blow down valves. And we got them set up on timers to come on periodically to send that product down to the drying beds, so that way the water stays nice and clear coming over.
The clarified water flows over the specially designed edge called a weir. From there, it heads to the next process. Recarb Basin.
Next up is the Recarb Basin, which is where water from the contact clarifiers flows into a basin where carbon dioxide is added.
Here, and then it feeds in right over there, and that's what helps lower down our pH. Start feeding in CO2 right here. We start feeding in CO2, and as the water's coming off the clarifiers at a high pH, it's coming across and it goes down and it comes around on a serpentine and goes this way. So it's going in a serpentine pattern, and you're feeding the CO2 in there to lower that pH. So the serpentine gives it contact time with the CO2 to bring the pH back down from like a 10.8 to an 11 back down to, like somewhere around a 9.2, 9.3, somewhere in that ballpark. So that way you're bringing that pH steadily down.
Postclarifier Ozone.
Remember that third supply line of ozone? This is the point at which it's applied, giving another round of disinfection.
Goes into the post ozone basin. So up there was so we're treating all the water when it first comes in off the raw side before chemicals. We're disinfecting with ozone, and then after going through the treatment process and the clean water coming off the clarifiers, pH being lowered down, then we're feeding ozone again for disinfection here.
Feeding ozone again. Okay, that
Right.
was that other one.
That was the pre, and now this is post. So this is the last time we feed ozone. But it's also disinfecting once again after the water's been treated. So now we're adding ozone again. And now that's what we have going on here. But this is with all the water not just one side or the other. This is all the water coming to the filter, gets disinfected again with ozone.
Mixed media filter.
Water enters these large rectangular water tanks from above. The bottoms of these tanks are lined with deep layers of filtration sand and media. Roy explained with this sample tube.
A little thicker, a little thicker, or a little bigger, a little bigger, a little bigger, and then you get down to like a rock or gravel size.
Yep, I can see that there.
Right.
It's almost like they had to put in rocks to simulate.
So that's why we call, instead of calling these sand filters, because normally sand filters has the same consistency of media or product in them, where these are mixed media because you're going from a very fine to a little bigger, a little bigger, a little bigger, a little bigger, and then down to rocks. So your water is going to move slower through here to remove more of your dirt and whatever's in the water. It's going to help remove it. And then it speeds up a little bit, it gets a little faster, gets a little faster, and then it gets really fast, and then it should be pretty clean.
When the filters need cleaning, they go through a backwash process. Water is pumped in from underneath, stirring up the media and whatever matter it is collected. The media is then flushed clean. Getting the media back in layers happens naturally because the larger media settles out first and the smaller media settles out last. It naturally falls back into the desired layers.
And then it comes into filtration. So now we're seeing, how much is coming into each mixed media filter, how much is going out, but most importantly, we're seeing how much NTU each filter has and how much NTU is leaving. And the reason why NTU is so important is because the removal to bring NTU down lower helps with your chlorine and disinfection.
What's NTU?
So NTU is just basically you're reading a particle in the water. So you're just reading the particles in the water, and it's picking up like your dirts and all your leftover stuff. So right now, like that's reading 0.176 NTU. So this is how many particles are kind of left over after filtration. Now some of this is going to get removed also when it goes to the granular activated carbon or the GAC. So it's going to reduce that down even further. But what you're trying to do is let the ODEQ in the state of Oklahoma there's regulations that say that your filters cannot go above a 0.3 or you have to run, or you're out of compliance basically with your drinking water. And the reason for that is because think about your chlorine. So when we feed chlorine or we're disinfecting, you have particles in the water, right? And if you have, say, like these little particles here, we'll say this here, all these little particles, these are your little NTUs. And then you have we'll say your chlorine or your, trying to come through here, and we'll give him little circles like this all over the place. Okay, and he's floating out there with these small particles of NTU. So you got your chlorine here, you got your little particles. Well, then you got your organisms or your bacteria that's trying to hang out in there, right? Well, the more NTU that's in the water, they act as shields. And they start shielding what the chlorine is trying to get to kill. So the more NTU you can remove out, the less shields it has for the bacteria has to hide behind so the chlorine can attack faster.
Gotcha.
GAC filters. The filtering process is not done yet.
The next stage is granular activated carbon, or GAC for short. You could think of these like a Brita filter. These filters remove organic compounds, including synthetic compounds, such as solvents, cleaning compounds, insecticides, and herbicides. There are 9 of these filters.
It comes into a pit over there, and then we use pumps to push it through the granular activated carbon, and we're pushing it through there to to help with taste and odor and remove more NTUs and things within the water. And once it leaves from here, it's heading its way to the clear wells.
Chlorination.
The chlorine gets added after the GAC filters. They use free chlorine as opposed to chloramine. Its entry into the plant is way back in the chemical room.
As to where chlorine is a little slower, but you want that residual there so that way when people are using water, it's still a residual, so nothing can grow after the water's been treated. So that chlorine residual is there in case there's a line break and dirt or something gets in, the chlorine will attack it and disinfect it. And so that way you don't disrupt or contaminate all your water in your distribution system. And keeping a good residual keeps down any kind of bacteria growth in the distribution before the water can be consumed for use. So it keeps it safe. Now on the other side of that, chloramine, it's a good disinfection, but it takes a long time to disinfect. As to where free chlorine acts very quickly, not as quickly as ozone, but it acts quicker than chloramine.
From there, it gets metered and mixed up in a separate area.
Over to here, and this is where we adjust how many pounds of chlorine we need to feed a day, whether it's 140, 240, 50 pounds, whatever we need to keep a good residual in the clear wells going out the distribution. We make that adjustment here, but the point where it feeds in at is before the clear wells, just after the GACs. So this is where it all gets mixed up, where you pull in the chlorine gas, mix it with water, and make a hypochloric acid. That creates your free chlorine residual to send over there, but it's fed all the way back across on that side of the plant.
And it does not get mixed with the water until a point after the GAC filtration and before it gets put into clear wells.
Clear wells.
These are the clear wells. They are large covered storage tanks for the water. The water that enters has been fully treated, including with chlorine, which keeps these tanks from having any bacterial growth. From the time the water left the lake until it enters the clear well is about 12 hours. That is 12 hours of cleaning, disinfection, filtering, softening, pH control, and all of the other processes to produce good, clean, desirable water. Rigorous testing ensures that the water in these tanks is safe for human consumption and ready for distribution.
Every shift runs a set of samples, so we're manned 24/7. So here's the first set of samples we run, and then 4 hours later we have to run another set of samples for one shift. And so this will be like your first labs, and then this little bit down here is like your second labs. And basically your first set of labs you're running, so the raw water that we talked about up there at the screen room, this is what we ran for. So we want to do the temp, pH, P out, T out, hardness, calcium, magnesium, hardness, turbidity, and conductivity. And we run that for the raw water coming in, the clarifiers, the recarb, which was where we feed in the CO2, the first finished, or the first filter, so that's where the water's coming into the filters, and then when the water's leaving the filters. So, or the first finish, or basically where the water's leaving, where the water's leaving going out to distribution, we pull water from there. And so that's basically where the end product.
Distribution.
A pump station transfers the water into the city's distribution network, which consists of the 56 supply wells, 8 water towers, additional ground storage tanks, over 5,000 hydrants, and 561 miles of piping. The system design not only provides a water supply and storage, its system of water towers uses gravity to create water pressure in the system and minimize the use of electrical-driven pumps.
The water leaves from here, heads out to distribution. When it leaves from here, we had a straight line over to I-35. So now this is the first stop after the water leaves the plant. We do send some water over to Post Tower, and over to Chitwood Farms on this side of town. Let's see, towers. So we do put water into Post Tower once it leaves it here. And so we only have 4 pumps at high lift. Reality is, if we didn't have Post Tower, which is right here on the hill, filling, we would need more pumps to push all the water over to I-35. But seeing as we have the tower, they put the tower there so that way we push water out directly in distribution. It fills Post Tower, but it creates head pressure to push the water on over to I-35 with not having to have as many pumps at high lift. Letting gravity work for you, because it's free and it's inexpensive if you can find a way to make it work for you. The only thing it costs is the tower, but the tower cost was, up front once it's built. That's it. And then gravity does the rest instead of electricity. So instead of having 8 pumps, we only need 4 because we have the tower. So it's a way of saving electricity and it being more friendly on the environment. And so the water leaves there, kind of builds the pressure, and comes into I-35. It comes in by way of this.
Look at the water towers, everybody. You can see there's waters in the water tower.
Yeah. So the water comes in by way of this polyjet valve, and it fills up in the bottom. And so now this storage tank, remember I talked about that earlier, having water out in town, and you're like, well, if you lost electricity here, what would we do? Well, I got a lot of storage out in town, so we got a lot of water stacked up in places, so we got some buffering room if we run out. And so the water fills in, and so now we got these 6 pumps that we can pull the water from here. And the water comes into this manifold, and half of it goes towards, X amount goes to northwest. So it goes to the north. It heads to the northwest side of Edmond, and then this here heads to the middle of town towards College. So it splits 2 different ways and towards 33rd. So this is what we're pulling out to push water on into town. This here, once again, is another tower. I want to say it's one of the taller towers in the state of Oklahoma. It's the tall tower at I-35, or it used to be at one time when it was first put in, but it creates extra head pressure, so you don't need as many pumps to push the water. So as the water's leaving, it goes up in the tower, creates pressure, helps push the water on out to distribution.
Control room.
You've already seen glimpses of the control room, but this is the hub for communication, as well as monitoring and operating the treatment plant and distribution system.
So when we run lab, we have some of our lab results down here. Over here is where we're feeding some of our chemicals. Some of these chemicals are set up to where we only want to feed like so many parts to come up with so many pounds per day of lime. So we're feeding 100 parts of lime per day at 4,731 pounds per day. Polymer, we're feeding a 2.2 dose at 104 pounds of polymer per day. Then here's how much carbon dioxide we're feeding. Here's our chlorine. We feed Aquamag. Now, Aquamag is basically orthopolyphosphate that is fed into the water, so that way when the water goes out to distribution, it lines the piping to give a protector, to protect as a protecting barrier to keep leaching from metals into the water. And so it creates like a layer of film that kind of protects the water from breaking down the minerals and pipes and the metal and leaching into the water and making it harmful for human consumption. Because not all pipes are made out of PVC. So you still have like certain ductile pipes out in distribution. You got some that are metal, you got some that are PVC. But you don't want leaching in. And what normally leaching comes in is when you have basically aggressive water, which is basically, we run an aggressive index, and if the aggressive index goes into the minus, the water becomes just a little bit on the acidic side, so it can cause leaching. But even if that happens, your polyorthophosphate has that coating there that will keep it from happening, even if it is a little bit high on the acidic side. When we look at each well, they're numbered. If they're blue like this, That means that they're non-chlorinated, meaning that we don't have to add chlorine to them. And the only reason we add chlorine is to help with the residual out in the distribution. So certain wells, when they come on, you can have it to where you're feeding a little bit of hypochlorite. It's not like what we have here. It's just a hypo, where it's already the liquid mix, like a heavy-duty bleach, and then that feeds out into the system to help boost the residuals and keep them up. And if it's in yellow, we have chlorine that feeds there. If it's in blue, that means that doesn't have chlorine feed. We have an alarm system. So for example, right now we're running well 23, and it's doing 205 gallons per minute. And its level is at 232. So that's the static level. That's how much water is in basically the pipe where the pump sets in.
Okay.
So that's the level. So it's 232 feet of water. And you're pulling 205 gallons per minute. And of course, those numbers fluctuate.
Building for the future.
When the lake and the treatment plant were built in the 1980s, the population of Edmond was about 35,000. Although it was built with future growth in mind, the 2020 population has nearly tripled, and growth is continuing. To meet the growing demand for water, a new water treatment plant is being built adjacent to the existing plant. Even the water intake capacity from the lake is being expanded. When the approved upgrades are complete, the new water plant will be capable of producing 30 million gallons of water a day, 2.5 times the present-day capacity of 12 million gallons per day. Thanks, Edmond Water Resources, for the tour and for all of your work providing water to the city of Edmond.
We learned a lot and gained a huge appreciation for what you do. See you next time.